All right, and this will be our third and final video, I think, on the chapter 9, which is about momentum and its conservation. And now that we've talked about momentum, I want to talk about how you change momentum. So changing momentum. And the topic here, changing momentum, is related to something called impulse, which we'll see in a minute, which is a new quantity for us. And I'll just remember or remind you of something I said in our previous video, which was that momentum is conserved unless there's an outside force acting on the system of particles, and so the short answer to how do you change momentum is by an outside force. Momentum of a system changes when an outside force acts. Inside forces internal to the system will not change the momentum of the system, but external forces or outside forces will change or can change the momentum of a system. And this will be sort of reminiscent of our unit on energy conservation. We said that energy is changed. A change in energy is due to something called work. And we had the so-called work-energy theorem, which said that the total amount of work done, work total, was equal to the change in energy of the system. And now what we're going to have is a similar relationship which is the change in the momentum. Delta P is related to this other thing I mentioned called impulse. And this will lead to the impulse momentum theorem, which says that the total impulse, which is abbreviated J, is equal to the change in momentum delta P. So let's think about, or let's get into what this impulse thing is. Maybe I'll just start with Newton's second law to kind of derive the expression, and then we can see it in action. So we know that F equals ma. And of course, we know that A can be written as dv dt. And now if I separate these variables, I can say f dt equals m dv. And if I integrate both sides, I can say that the integral of f dt is equal to mv minus mv naught. This thing over here, of course, this thing is our change in momentum. That's what this is. This is delta P. And that means that this thing over here is the impulse. This is impulse J. And so that tells us what impulse is. I'll write it over here. Impulse, which is abbreviated J, is equal to the integral of f dt. So just like if we go back to the work energy theorem, remember that work, we noted, is force times distance. That's the principal way of calculating work. It was the integral of f dot dx. And here, impulse is force times time, or the integral of f dt. In some cases, of course, what we'll find is that the force is constant, or you're given an average force, in which case it's really fairly simple. If you have a constant or average force, then the impulse J is just equal to F times delta T. And that's the simplest case. For instance, just to see maybe we'll start with the simplest case to try to get a sense of what impulse is all about. Like, let's imagine, for instance, that I don't know, you're in a building here, and there's a fire in the building, and you're going to jump out the window. So this is the window right here, and you're going to jump out the window. And if you were to, so I'll try to draw you. Here you are. You're thinking about going out the window here. When you land, you are going to have a certain amount of momentum when you land here. You're going to land. And you're going to have a certain amount of momentum when you land, and that momentum is going to go from whatever its value is the instant before you landed to 0. You will stop. So there will be a change of momentum from your velocity when you're just about to hit the ground down to 0. And the way your momentum is changed depends on the nature of the surface that you come in contact with down here. So for instance, this could be pavement, right? This could be like concrete. Could be very, very hard surface. And what that means is that if it's a very, very hard surface, this momentum change is going to happen over a very, very small time. You will almost instantly come to a stop, which means that the force has to be very, very large. Big force, small time equals a change in momentum. On the other hand, if, I don't know, maybe there's like a pile of leaves here, or maybe there's a snowbank, right? If there's a snow pile right here that you're falling into, that snow pile is gonna allow for some give. You're not gonna stop instantaneously. You're gonna be more gradually stopped. In other words, the delta t here, I should write delta t. The delta t is going to be larger. And when the delta t is larger, that means that the force can be smaller. And so you can see, of course, if you were to be jumping out of this window, you'd be very happy to land in the snowbank, where the impulse would last a longer time, and therefore the amount of force imparted on your body would be smaller. So this is an example of how impulse momentum theorem can be sort of applied to everyday life. This is why, we use airbags, and why boxers wear boxing gloves, and so on and so forth, to increase the time of impact and to thereby decrease the amount of force of impact. Now, in reality, when you have an impact like this, if you were to jump and land either in a snowbank or on the concrete, the truth is that the force is not going to be constant. The force is going to vary. So, for instance, in a collision such as this, if we made a graph of force as a function of time, you're very likely going to see something like this. Initially, the force is very, very small, and then it's going to increase to some maximum value and then decrease in some way. Try to make that a little bit smoother, maybe something like this. And so here we can see that the force is varying, and there'd be some sort of complicated equation to explain the force as a function of time. But what we can note here is on a graph like this, so this is f as a function of t, since the impulse is the integral of f dt, that means on a force time graph, we know then that the area under this curve is going to give us the impulse. So this area, I'll shade it here, is going to be equal to the impulse. Whatever this area is the impulse. So area is equal to the impulse, and therefore it's equal to the change in momentum. So you should be on guard whenever you see a graph like this where it's f as a function of t. That should give you a clue that what you need to be dealing with here is the impulse momentum theorem. You're going to integrate that or find the area under the curve. Oftentimes what you'll see is you'll be given another way you might see a problem is you might be given a situation where you're told that the force as a function of time is some polynomial, like 3 t squared minus 4t cubed plus 5 or whatever. And if you ever saw this, that's another sort of clue that what we're going to deal with here is the impulse momentum theorem, that you're going to take the antiderivative, you're going to integrate 3t squared minus 4t plus 5 from 0 to t, and that's going to give you mv minus mv initial as an example. One thing to be careful about here that I think we have to recognize, and I really should have done a better job of indicating this up here, momentum is a vector, so impulse is also a vector. I really have to do better about indicating that using our notation. This is a vector quantity. When you're calculating the impulse, it is a vector quantity. That is to say that you do have to be mindful of the direction of the impulse in terms of telling you how the momentum changes. So if the impulse is positive, that means that the impulse or that the momentum is going to increase in value. And if it's negative, that means that the momentum is going to decrease in value. But unlike with the work energy theorem, we do have to be mindful of assigning positive and negative directions always. Maybe we could try a little bit of a practice example of how we might use this. And maybe just for kicks, we'll try a two-dimensional system. So maybe we've got a baseball, and we'll say that this baseball here, we'll say it has a mass of 0.5 kilogram, and it's moving, let's say it's moving this way with an initial velocity that's in the x direction, so it's just moving horizontally here. And I guess we could say what? We'll say it's moving 20 meters per second. And then let's imagine that as the baseball moves, it gets hit by a bat. And when it gets hit by a bat, it experiences an impulse from the bat. So we'll say that like here's the bat hitting the ball. It's going to experience an impulse, and that impulse, I guess I'll give the impulse in vector form. I'll say J is equal to, let's say negative, maybe 100t plus 20 I hat plus 50t plus 10, 50t plus 10 j hat. So what if I then asked here, what is the momentum? What's the momentum P at t equals 0.2 seconds? Maybe that's the question that we're going to ask. So what I have to note right away is that there are two dimensions to this problem. So there's going to be an impulse in the x direction and an impulse in the y direction, and that total impulse J is going to be equal to the change in momentum. So let's go ahead and calculate the impulse by using our impulse equation. So I'm going to take the integral from 0 to 0.2 of this whole thing up here. That is of negative 100 t minus 20 I hat plus 50 t plus 10 j hat. And that's going to be equal to the change in momentum. So if we were to do this out here, what's this going to be? This is going to be negative 50 t squared minus 20 I hat plus 25t squared plus 10 j hat. We're going to evaluate that from 0 to 0.2, and that's equal to the change in momentum again. So what's this going to be? T squared is 0.04, so that's going to be what? Negative 22 I hat, and this will be plus 11 j hat is the change in momentum. So then I have to think about, I have to ask myself, okay, well, what is the change in momentum? Well, it's going to be the final minus the initial, but of course, initially the momentum here, P initial, if I were to write this, the P at the start, or P at t equals 0, I should say P naught, is going to be 10 kilogram meters per second I hat in the positive direction. Again, I'm calling to the right the positive direction. So that means that the final momentum, P final, which is P at t equals 0.2, is going to be equal to P naught plus J, the change in momentum. So P at 0.2 is going to be equal to P naught plus J, the change in momentum. And that comes directly from the impulse momentum theorem. So now I'm going to note that P naught was, I forget, what did we say it was? 10 I hat. So I'm going to say 10 I hat plus negative 22 I hat plus 11 j hat. And that's going to give me a total of negative 12 I hat plus 11 j hat. That's the momentum, P at 0.2 in vector form. So a little bit weird, it's been a little while since we worked with vectors, so this might feel a little bit unusual, but that's how we might deal with this in a two-dimensional situation, which, just so we're clear about what those directions mean, it just means that the ball, after being hit by the bat, is going to be moving in the negative x direction this way and the positive y direction that way, right? So it's going to be moving up at some angle here. All right, I think that's enough for this video. Excuse me.